So some applications of the fundamental theorem of calculus. So just a brief overview of it first. We've got some function, it's continuous on an interval. And then we define this other function, I'm calling it a. A lot of times you'll see the notation for this to be capital F of x. And remember that a definite integral, which we have over here, is the result of a Riemann sum after we take the limit of it. And what that means is it adds stuff up. So we could call it an area function. Is one interpretation based on this graph here. You could call it an accumulator. It accumulates stuff. So sometimes we call it capital F. I like to call it A in this case. Either way, it's the result of adding a whole bunch of vertical values with a little tiny width on each one. Now, the first part of the fundamental theorem basically says that the rate of change of that accumulator function, the area function, is the boundary function at the top. So as x increases here, the rate of change is dependent upon the upper boundary here. Seems pretty obvious when we look at that, hopefully. The fundamental theorem part 2 basically is a consequence of this here. And what this tells me is that I have a relationship here in terms of antiderivatives. If the derivative of A is f, then the antiderivative of f is capital A. And so what the fundamental theorem of calculus ultimately tells me is that a definite integral from one boundary value to the other of a function can be resolved by finding any antiderivative, evaluating at the upper endpoint and subtracting the lower endpoint. Some nice consequences of that. F is A prime, so I can substitute an A prime in place of the F here. So this is the first beautiful consequence in the theorem. So the net change in a function can be found by integrating its starting point to the ending point. Okay, so that's net change here. The other kind of cool thing about it is that since our function is defined as an integral, A prime or capital F prime, the integral cancels the derivative. Now, important things about that, it starts with ends with x, and technically I here, since is represented an endpoint, then I should use it. So we usually throw a dummy variable. It could be t, it could be u, technically. So this is an important. So we're just going to look at evaluating some consequences of the fundamental theorem, parts 1 and 2. So first, here I have a function from 1 to x of the sine of p to the 5th. And that's not the function I want. Oh, why did I write that down? Sorry, I'm going to look back on my notes here. Interesting. Oh, I know what it's missing. It's supposed to say find the derivative with respect to x of that same thing down here. Derivative with respect to x. So we're getting at that consequence that the antiderivative and derivative, the definite integral and the derivative undo each other. So in this case right here, the result, according to the fundamental theorem part 1, is just going to of x to the 5th power. Now we could, let's see, actually in this case we can't use the theorem fundamental theorem part 1, and that's it. All right. Applying that same thing here, now I have a constant at the bottom, that's all right, but I have something other than x up here, and I'm taking the derivative of it. So what happens here is I have to think about the chain rule applied. So when I take the derivative of the integral, they sort of cancel each other out. So I'm going to get a cosine of 3, and then the upper variable endpoint sticks, so that's going to be an x squared there. Plus, evaluating the upper variable would be x squared. And the catch here, because that's not just an x, the chain rule says you have to multiply by the derivative of that inner function, and that upper bound is the inner function, so I'm going to have a multiple of 2x there. So here, it was just an x at the top, straight fundamental theorem, derivative and integral basically cancel each other. Here, it's almost a cancellation, but I got to use the chain rule because of this more complicated upper bound. All right, let's see what else we have here. In this case right here, we're going to use a trick to solve this one. So first, let's consider this function. So my inner function is f of x equals the square root of 6 squared minus x squared. And you could plug that in a graphing calculator and say, well, f of x is just a y value. So I'll get the square root of 6 minus x squared. And then I'm just going to get rid of that square root for a moment. And this is going to help me with my integral. So then I get y squared equals 6 squared minus x squared, and bring the x squared over, y squared plus x squared equals 6 squared. This is a circle. The center of the circle is the point 0, 0, and the radius of this circle is 6. So looking at the graph of it, at least this is the upper portion because it's the positive square root. So here's 6, or negative 6, here's 6, here's 6. Then this is the function I'm looking at. I am using the definite integral here, so that means I'm trying to find the area under the curve here. So I have the area of a semicircle. Other thing to consider is this is an even function. Even means that f of negative x, the negative doesn't make a difference. That's the same thing as f of x. So if we replace x with negative x here, if you square a negative, it stays, just the square kills the negative. So that doesn't change anything here. So this is definitely even. Even symmetry is also symmetry about the y-axis. Cool thing about even symmetry is you can rewrite this and say this is twice the integral from 0 to 6. Boundaries are easier to evaluate. Square root of 6 squared minus x squared. Now, unfortunately, there's no simple antiderivative for this sucker. However, I have a geometric means to do. So right here, I'm now considering just this quarter circle. And normally, the area of a circle is pi times the radius squared. I want a quarter of that. So I times 6 squared over 4, which is 36 over 4, 9 pi for the area of that quarter circle. So here then I'm going to have twice 9 pi, or 18 pi, would be the result of this original integral. So knowing something's an even function can be nice. I'll do this one a couple of different ways here. It looks like I'm going to take that to a new page. We're running out of room. And there we go. And one more time. There we go. So here, let's consider the sign for a moment. Color. The sign starts off at the origin, and then 0 pi over there, and it drops down, and back up over there. I mean, we have pi over 2, negative pi over 2, sorry, and pi over 2 over there. So this is what we call an function. F of negative x is equal to the opposite of f of x. This is also symmetry about the origin. Cool thing about odd symmetry is that if you use symmetric boundaries on each side, you get an area over here that's negative, and you get an area on the other side that's positive. And if the boundaries are symmetric, then they cancel each other out. Well, we do have an odd function here with symmetric boundaries, so that means this is definitely a 0 based on the geometry of the situation. All right, so let's evaluate it using the Fundamental Theorem Part 2. Fundamental Theorem Part 2 says that you just need an antiderivative for that. So antiderivative of the sine, you might start with the cosine of x. However, the derivative of the cosine is the negative sign. That means I want to put a negative in front. So if I take the derivative of the negative cosine, I'll get the opposite of the negative sign. Evaluating that from pi over 2 to negative pi over 2, we get the opposite of the cosine of pi over 2 minus the opposite of the cosine of negative pi over 2. Considering the cosine function peaks here, drops down, keeps dropping down, and then it starts to rise again, and it does similar stuff on the other side. So here I have a complete cycle from here to here. That's going to be a distance of 2 pi, so this side is pi, this side is negative pi, and we bottom out right in the middle at pi 2. And here, negative pi over 2. So the cosine of negative pi over 2 is 0, and then we have minus a negative or plus another 0, so we get 0 in the end. So sometimes realizing a function is even or odd can help simplify the work that has to be done, which is kind of nice. All right, what else do we have here? All right, here's an interesting homework problem that you have, acceleration. So let's suppose it's equal to 6 times the sine of t. We have an initial velocity iterate to find out a few things. It's the velocity displacement. So just remind acceleration is the derivative of velocity, and velocity is the derivative of displacement. That change theorem to work on this right here. So for part A, we are going to find the of 6 t dt. That antiderivative would be the opposite sign of t, because remember the derivative of cosine is the negative sign. So we get up here. Then I have a plus c. Now this right here, because I took the integral of the velocity function, excuse me, acceleration. And so that was the integral of the acceleration function, which is the integral of the derivative of velocity. That's going to give me a velocity function. Now, I do have this constant to figure out here. And so the key there is that v of 0 is negative 8. So putting that together, I get negative 6 times the cosine of 0 plus c equals negative 8. Cosine of 0 is 1, so that gives me negative 6 plus c equals negative 8. So then c is going to be 2. So now I have b, because I know my velocity function. Velocity function is negative 6 cosine of t minus 2. Next part of this, to find the displacement. So displacement is found by integrating the derivative of displacement over time, in this case from 0, 3, to, well, velocity is that derivative. So I want to find the integral 0, 3 of negative 6 cosine of t minus 2 with respect to time. So I have to come up with an antiderivative here and then evaluate the inputs. So let's bring that to the page. So we need an antiderivative for that negative 6 cosine of t minus 2, which would be the opposite of 6 times the sine. Remember, the derivative of sine is cosine, so needs to evaluate that from 0 to 3. So that's just displacement. So that's going to give us times 3, take away parentheses, negative 6 times the sine 0 minus 2 times 0. And so it's worth writing this down. Don't take it for granted that because 0 is the boundary, all of this is going to go away. It kind of depends on the function. It does depend on the function. Well, it turns out the sine of 0 is 0. So all of this is a big 0. So I just have this stuff over here. So I have negative 6 times the sine of 3 minus 6. So that right there is the value that I get for the total displacement. Of the net displacement, excuse me. And we can plug that into a calculator and get an evaluation of it, which probably would be a good idea. So let's see. Calculator. So I have negative 6 times the, let's see, sine, is that right? Yeah. There. Let's do that, try again. Negative 6 times sine of 3 minus 6. That gives me about negative 6.3-ish. Which seems reasonable because this sine is going to give me a value between 0 and 1. So it's approximately negative 6. Next question. Back here, we also want to find the total distance traveled. Now, that's different than the net displacement of the object, which the antiderivative integral gives me. Because here, if the function's negative at any point in the interval, that cancels out with positive parts in the net displacement. So the total distance means I have to find the absolute value of all this stuff. So I got to see if that original velocity function changes sign anyway. So, new page, my velocity function, remember, was equal to negative 6 times the cosine t minus 2, right? And let's start off simply by just finding its zeros in the region I'm interested in, and the region I'm interested in from 0 to 3. So let's see, we'll add 2 to the other side, so negative 6 cosine of t is equal to 2, divide by negative 6 cosine of t equal to negative 2/6 or negative 1/3. All right, whoa, crazy that. And so I'm just going to think about that geometrically for a second. Cosine on the unit circle is an x value. And so here I would be considering there's -1 for x, there's 1 for x, so 1/3 is about here, or -1/3. -1/3 could be that value up there, it could be this value up here. So I have the arc cosine of t equals the arc cosine of -1/3. So t is going to be an angle here in radians. And so one possibility is that angle over there. Another possibility is this angle over here. And I'm not going to go backwards for this angle, because that would be negative. Okay, so this angle here, that one there. Parentheses. Let's get a value for the arc cosine approximately. Calculator. What is the arc cosine? Let's see. Cosine of -1/3. All right, so give it to me in degrees. I would apply that by pi and divide by 10. Yeah, so it's about 1.9-ish. So calling it. See in the calculator. Arc cosine. Okay, so this one gives it to me in radians. So yeah, about 1.9-ish radians. Say same thing. Yeah, about 1.9-ish. So we have one answer. So another, so approximately 1.9 radians. So if this answer on the top is 1.9 radians, down here it would be 2 pi minus that. So the other answer here is going to be 2 pi minus arc of these. Again, go. That evaluates 2. So that looks like it's going to be outside of my interval. Desmos. So let's give it a name. Let's call it A. So then the other possible answer is 2 pi minus A, which is for something. That one's outside. So this just in our interval just changes once. At the arc cosine of 3rd. So what that means is I have to change the interval. So I'm gonna integrate at first from 0 to this value. Let's call it A for now, for my first angle, and I'm integrating -6 cosine minus 2 dt. So that's going to give me the first part. Double check that that's positive. Let's see. So if I were to plug in, I have to check which part's positive and which part's negative. Brackets, we have -6 times cosine of t. Twice. There's no so there's my function there. So it is negative in the first part, and there's my 1.9-ish intercept, and then it's positive after that. All right. So drawing So the first part is negative, so that means I want to take the opposite of all of this, and then I'm going to add on the integral from a to 3 of the original function, 6 cosine of t minus 2. And there's really no other way to deal with it because absolute value of a function is complicated. You've got to break it up into the positive portions and the negative portions. The nice thing here is that negative flows through there. Try a smaller one. Perfect. So this negative is going to change the sign here and here, where a is the arc cosine of negative 1/3. Now the antiderivative is pretty similar, except we just have some sign changes. Technical difficulties. So antiderivative, remember, is just going to be, for this one, with the sign change, is just going to be 6 times the cosine sine t plus 2t, and that rated from our special value to 0. And then next is going to be, that negative sticks around, 6 sine t 2t. That one is evaluated from 3 to a, or 8 to 3. So now it's a matter of just plugging in those numbers, and this is a calculator problem at this point to get the rest of it. So where we had a negative result before, if we look back at that graph here, we were graphing over to x equals 3, that green line, you can see we have a much larger region over here than we have over here, and so the net result is negative. What the absolute value does in breaking that up means we're just going to calculate this area but call it positive and then combine it with that, so we'll get a good positive number in the end. So let's see what we get. So putting that all together, we have 6 times the sine of a, which I typed above already, plus 2a. Evaluate that at 0, the lower bound. Each of these is 0. Okay. So I can skip that, and then I'm going to have a plus, I'm going to put a parentheses. I have a negative 6 times the sine, and we pick the upper boundary here, which is 3. Putting in a 3 here, and then I have minus 2 times 3. And then we'll subtract the lower bound, parentheses, negative 6 times the sine of a minus 2 times a. Parentheses, close parentheses, and I get a net result of about 12 units altogether. So about 12.1 evaluates to. All right, so that's it for now. Good luck with your homework. Have fun. Do good math.